So we're going to continue on from the last topic of diffraction by looking at interference. And as we talk about interference, hopefully your understanding of what I was talking about with the diffraction gratings will crystallise and will make a lot more sense. Because the two are very, very closely related. It's a little hard to separate them out, really. So interference, basically this is something that can occur when two waves of the same type occupy the same space. So mostly we're just talking about having two sources of waves here with this, and what it creates when I've got these two sources of waves is an interference pattern. And if you look at this water wave here, you can see that there are bits where it seems really smooth, and then there are bits where there are much larger waves, and it sort of alternates. And if I were to kind of just look along here, it kind of goes small, big, 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 small. And we get this alternating pattern of what we call maxima and minima. And those are caused by regions of reinforcement and cancellation, which we looked at when we talked about superposition. So that thing that was really short, cropping up again and again, has been very useful. Okay. Now the other thing I talked about in the diffraction video was path difference, and I'm just going to crystallise that for you a little bit as well. So path difference is the difference in distance travelled by two waves. It's often measured in wavelengths rather than meters. So for example, two waves travel from A to B along different routes. They both have a wavelength of 2 meters and the two routes differ by a length of 8 meters. We would say that their path difference was 4 wavelengths, or 4 lambda. Now we could also talk about phase difference, and we talked about phase when we met waves, and that's just looking at what different point in the cycle the two waves are when they meet. So if one is at peak and the other is at trough, they are out of phase, 180 degrees out of phase. Or if they both arrive in a peak, they would be in phase. So in some ways that's a lot simpler because we've already talked about path difference, but we could apply it here as well. So if these two waves here, if they started off in phase, they travelled a whole number of wavelengths, then when they reach their destination they would also be in the phase. So it's almost, like I said, a little bit simpler than talking about how many wavelengths different their path is. But it amounts to the same thing really. Just make sure you either talk about one or the other. Don't mix and match. So what I will do is when we're in class, I'll let you experience this. I'll set this up. But I can create an interference pattern with 2 speakers. Set up 2 speakers playing the same sound with a distance between them. We end up with these loud and quiet spots. So just to explain what's happening, it's just the principle of superposition. So if we just look at a couple of different situations, we can figure out what's happening at all the points. So if we are at a point where the two waves arrive at that point in space and they are in phase, or they have travelled a whole number of wavelengths different for their path difference, when I combine them together I will get reinforcement and I will get a much larger resultant, so I'll be in a loud spot. Now if the two waves have travelled a distance that is a whole half number of wavelengths different. So for instance, this one, the green one, travelled half a wavelength further, or 2.5 wavelengths further, or 3.5 wavelengths further, then they will be 180 degrees out of phase. So when this one's at peak, this one's at trough, and they're always completely out. So when I then add them together, I end up with nothing. So I get cancellation. And often that will be 0 if they are perfect and there's nothing else going on. In an ideal situation, I would get perfect cancellation. I might just get minimum if it's not quite perfect. There's all sorts of reasons it might not be. So I might just get a quiet spot rather than a silent spot. Now, if my waves are different amplitudes, I still get this effect. It's better when they are exactly the same, but I still get the addition even if they're different amplitudes. That's just what the third one is showing you, that I can still get this reinforcement and cancellation. Okay, right then, as well as sound waves, we can do this with a laser, and at this point I want to point out that it is spelt L-A-S-E-R, not a Z. It's not an acceptable spelling, even if you're an American. because laser is an acronym. It stands for something. It stands for light amplification by the stimulated emission of radiation. Stimulated, not simulated. So it does have to be an S, please. Do be careful of that. A laser is useful for doing this. Bath time again. Sorry, that's what I get for recording in a room with chinchillas. What was I saying? Oh, laser light. We use the laser light for this because it is a source of coherent monochromatic light. Monochromatic we already talked about, means single wavelength. Coherent means that all the waves start off in phase. That's what it will be from the laser, but coherent can also mean that they have a constant phase difference. So they don't necessarily have to be in phase, but the difference between them is constant. Okay, so if I want to see this interference pattern, what I can do is I can set up a laser. For instance, if I shone it through double slits, so just split it into two slits, so it gives me two sources, and then go to a screen, I get a pattern that looks like this, and you can see we get these alternating bright, dark, bright, dark, bright, dark spots, just like I showed you with the water wave. And that is interference with light waves. I could do the same thing with a microwave probe. So if I've got a microwave transmitter, I can use some metal sheets to create some gaps so that I've got two sources, and then I've got my microwave receiver at the end. And if I move my microwave receiver from one side to the other, so sort of along this line here, I'd find it goes through peaks and troughs, so maxima and minima, just as before. Okay, so that is all we're going to talk about so far with interference. We're going to look into interference with light more specifically in the next video, which is called Young's double slit experiment. So we will talk about this a little bit more, but you've got the basics now, so we can start building on the ideas that we already had. Okay, so remember, any questions? Ask when you see me.